Hi. In this section, we'll take a look at other ways of inductively defining sets and how recursion is used to define functions on them. Basically, what we'll be doing here is we're essentially expanding our repertoire of inductive ways of defining sets. We have 3 already, we'll get a few more. The next type of inductive definition is a slight generalization of closure under a function. For any relation R over a set A and a subset X of A, the closure of X under R is basically all those elements that can be reached from X by following the arrows in the relation R. In the inductive definition, we add at each step the image of the previous set under R to the result. Let's look at an example. Let C be the set of all lowercase characters from A to Z. The relation we're interested in, R, is a relation over the strings, the finite sequences in C. It relates any string S in C star to the string that consists of any character from C, followed by the string itself, followed by the same character again. With that, what do these closures represent? The sets of odd and even length palindromes in C, that is, strings that read the same left to right and right to left. How would one express the set of all palindromes? Like this. Before we proceed to the next inductive construction, we first need to generalize a little our notion of image under relation to relations of arity higher than 2. For an n-ary relation, the image of an n-1 tuple under it is the set of all elements of A such that the n tuple consisting of first the n-1 tuple and then the value in itself is in the relation. Of course, just as before, this extends to sets of n-1 tuples in the same way as our original definition of an image. The bottom line is, when computing an image under a relation, whether for binary relations or relations of higher arity, we treat the last, that is the rightmost position, as the quote-unquote output, and all other positions in the tuple as quote-unquote inputs. Now we can proceed to our last inductive construction. It generalizes the closure under a relation by using multiple relations at the same time. Also, those relations may be of different arity. R is now a set of relations Ri, each of arity Ni. Given some subset X of A, its closure under R is, as you would expect, the smallest set Y that includes X, and that is closed under all the relations in R. Here, closed means that the image of any combination of values from Y under any of the relations in R is contained in Y itself. The construction follows the familiar pattern of inductive set definitions. We start with x and add in each step the images of all the combinations of values from the previous step under all the relations. Let us again look at an example. For simplicity, our character set is some standard set of characters, and we have three rules over strings of these characters: R1, R2, and R3. The first, quote-unquote, adds, if you will, a minus sign to the front of its single input string. The other two take two inputs, they are three-ary or tertiary, to produce an output. R2's outputs with an open parenthesis, then its first input string, then a plus sign, followed by its second input string and a closing parenthesis. The last rule is similar, except that instead of the plus sign, it uses an asterisk. V is the set of all non-empty strings of lowercase alphabetic characters. Let those be our identifiers. So with this, what's the closure of V under R? The closure of V under R is the set of all strings that look like expressions with lowercase variables and the operators unary, minus, and binary plus and star. Computer science is packed with examples of these rule-generated closures. Grammars describing programming languages, for example, and also many data structures. That's why recursion on sets of things created in this way, so-called structural recursion, is of particular importance. Take the little language we just defined as a closure of the set of basic elements, the variable symbols in V, under our three simple rules. Suppose we wanted to define a function that evaluates such an expression. In order to assign a value, for example a real number, to such an expression, we need to have values for all the variable symbols in it. This is our function e, which gives every variable, no matter whether it occurs in the string or not, a value in the real numbers. Our function eval e will assume an e and then map every expression in the language closure of V under R to a real number. And that is how we can define such a thing. Note how the case conditions destructure the original argument of eval e, and how the recursive calls operate on smaller sub-expressions. If you think back to the inductive definition of this set of expressions, note that whatever yi an expression quote-unquote appeared in for the first time, if it has sub-expressions, they would have to appear in any of the earlier yks. As practice, try to write a function that maps every expression to the set of variable symbols that occur in it. In order for this kind of recursive definition to be well defined, we need something called unique decomposability. To understand its importance, let's look at a slightly modified example. It only has two binary operators, plus and minus, and does not use parentheses. Consequently, this is a structurally recursive evaluation function. What might be the problem with this function definition? It does not uniquely decompose every string it might be applied to. For example, if applied to A minus B plus C minus D, it could decompose the string in 3 different ways on any of its 3 operators. Suppose we have a set R of generators and a subset X of A. Then this is the general form of a structurally recursive function definition over a closure of X under R. For it to be well defined, every value in its domain must, quote unquote, match exactly one case, which, if you look at the case conditions, means that every value can only be constructed by one rule from a unique combination of other values in the closure. Such is not the case for a string like A minus B plus C minus D, which can be built in more than one way using the generators, and that is exactly what makes it unsuitable for structural recursion over it.